I'm Reynolds Monick from Wagner Associates. Our ATS project focuses on using AI to optimize theater undersea warfare search effectiveness. The assets used are marine patrol and reconnaissance aircraft, such as the P-8 shown on the lower right of this slide, surveillance systems, ships, and submarines. Ironically, the United States had very good tools for this in the 1980s, in particular the BPCAS computer-assisted search software developed by Wagner Associates. But this capability wasn't maintained after the U.S. won the Cold War. Now that there is a recognized peer submarine threat, these capabilities need to be reconstituted. For 60 years, Wagner Associates has been applying sophisticated mathematical techniques to difficult problems to improve probability of mission success, in particular for the United States Navy. The key technical areas that we've worked in are mission planning and resource optimization, of which Atrius is an example, artificial intelligence and machine learning and reinforcement learning, and target tracking and multi-int data fusion. My key resources are offices in DC, Norfolk, and Philadelphia metropolitan areas, all of which have GENSER facility clearances. We have 35 technical staff, 14 of whom hold PhDs in mathematical science. Our SBI transitions to programs of record for a small company are very impressive. These include the Undersea Warfare Decision Support System, which is used for mission planning at the theater level, as well as on virtually every USW-capable U.S. Navy platform. The Acoustic Mission Planner, which is on all of the MH-60 Romeo helicopters in the United States and also many friendly countries. The Mine Warfare and Environmental Decision Aids Library, known as METAL, and MineNet Tactical, which is used for all the mine warfare planning. A mine avoidance system that we transitioned to submarines as part of APB-09, and a data fusion for torpedo defense system that we transferred through the ACB program in 2013. We also have recently transitioned a data fusion system to the Mark 18 uncrewed underwater vehicle. Modern, stealthy, and capable threat ASW capabilities pose significant increased challenges to friendly undersea warfare missions. Since we have limited assets, we need to optimize the effectiveness and efficiency of all of these missions. And in particular, we need to improve the exchange of critical planning, execution, monitoring, and assessment data between the TASWOC, which is the operating center for theater USW, the TOC, which runs the MPRA, and we need to optimize the use of the MPRA in theater USW. Current mission planning processes are manual and time intensive, and automating these processes will greatly reduce the time needed for mission planning, allowing the operators to concentrate on other important areas, and will also provide more effective, consistent plans. The way Atrius contributes to making this process more efficient is shown in the diagram at the bottom of this slide. It will, over the web, in this case CIPRNet, allow the planners at the TASWOC to develop plans and allow the TOC and the MPR planners to look at these and provide their judgment and allow for an iterative approach to collaboratively produce the best areas for ASW. This slide shows how the Undersea Warfare Decision Support System with Atrius enhancements will optimize Joint Theater USW by recommending search areas. In this scenario, we have one threat submarine coming out of Port 1 going through the Florida Straits, one threat submarine coming out of Port 2 and going between Cuba and the Yucatan Peninsula, and one submarine on patrol. The idea here is over a designated time period to maximize the probability of detecting these submarines. Each 8 hours, you have 4 MPRA that are available to search. On the left side, you see the locations of these submarines at time 0. We're searching from time 0 to time 8. And so you can see that for the transitors, we're leading them because over that 8-hour time period, they're going to move into the areas that we're going to cover, and that's the best way to maximize the probability of detection. We also want to, over the time period, detect the submarines before they get to the straits and into the open oceans. These estimated motion models could be based on intel, or they could be based on capability, and we are just trying to cover the possibility that they might be, coming out to attack. On the left, we have the situation at time 0, and as I said, the searches for the first 8 hours. On the right, we have moved the targets forward 8 hours, so this is their estimated location at time 8. But in this case, we've also included the negative information from assuming that these searches over the first 8 hours did not detect the target, which is always the way you maximize the probability of a plan over a particular time period. To do that adjustment, we use Bayesian statistics to apply what we call negative information. We determine the likelihood that the target would have been detected if it did go through one of those search areas, and therefore reduce the probability of that event, and then reconfigure so that we have the best estimate for the target given the negative information. Searches are optimized over the next 8-hour period, so they start at time 8, which is the position for the targets, and they end at time 16. Our current status on Atrius is that we have developed new and effective algorithms, software, and architectures for computing the operationally relevant metrics, including the overall probability of success. We developed tools for generating and automatically exchanging acoustic search effectiveness, generating and automatically exchanging the TASWOC's intent and situational awareness information in order to support mission type orders. We have tools for generating and automatically exchanging collaborative and iterative plans that will evaluate and optimize synergistic acoustic and non-acoustic search. And we've can automatically monitor MPRA operations in the TASWOC to support an adaptive near real-time response. Going ahead, we'll have an independent government evaluation in the USWDS cloud and integrate into USWDSS. Some key features, advantages, and benefits of Atrius are the novel algorithm, software, and architectures for exchanging data to support collaborative and iterative planning and mission execution. Novel algorithm, software, and architectures for optimizing those plans and sharing them among the TASWOC, TOC, and MPRA. In particular, by choosing search areas that most contribute to overall mission success, which might not be the best operating areas for MPRA in all cases, to provide the data relevant to optimizing search effectiveness to the MPRA so they understand their place in the operation, to get the relevant data back to the TASWOC to optimize future searches, and to fully exploit the synergistic acoustic and non-acoustic sensors. The benefits should be improved USW mission effectiveness, reduced risk to friendly assets, and reduced operator time on task. Our transition into the fleet should be fairly straightforward because we're already working with USWDSS, and they are the sponsor of both USWDSS and this SBIR. The additional transition paths that we have are the foreign military sales versions of USWDSS, of which we expect there will be several in the next few years. USWDSS is also going on the new frigate, and so capabilities tailored to single ships will be added to them. This could also go on the CBTSC, which plans carrier air missions for 5E, and similar algorithms could be applied to MTC2, D6N, the Commander undersea surveillance, and potentially search and rescue and counter-narcotic search and surveillance, since one of the key components that we've developed here is the optimal search planning, and all of those systems need that kind of optimal search planning capability. If you're interested in these kinds of optimal resource allocation problems, and think that the tools we described could help you, please contact us. I'm the point of contact for follow-up, and I have my cell phone number as well as our office number below. Thank you very much.